start now with deep generative modeling, where we will look at more examples of advances of the convolutional neural network architecture for image classification and other image tasks. Now, I would like to start with a quick interactive example where we have these three different images of faces, and we can look at each of these faces, and a lot of them seem extremely realistic. And A, B, and C, it may be difficult to determine which is actually real. However, in fact, we actually generated all of these images, and none of these people in these images actually exist. This was done by using one of the architectures we're going to be going through today, and by training that kind of architecture on facial data, it was able to generate these extremely realistic images. And to start, I'm going to introduce the concept of supervised versus unsupervised learning. What we've been covering so far has been called supervised learning, where we have a data X and a label Y, and we want to be able to map input data X to its correct label Y. And this allows us to have classification, object detection, as well as other tasks. On the other hand, unsupervised learning is where you only have the data X and there are no labels. We want to learn the structure of this data and the underlying structure, allowing us to have feature detection, dimensionality reduction of images, or clustering of different data points for classification. And with generative modeling, what we can do is take an input of these training with unsupervised learning, and we can have some certain distribution to create a model that represents that distribution. For example, with density estimation, we can take our different samples of the points, and we can create a graph that represents where more points are concentrated specifically. And with sample generation, we can take some input samples with this density estimation in order to generate new samples of images, for example. And our goal is to learn these generated samples so that way they can become more and more similar or realistic like the input samples. And with generative models, they are extremely important as often we want to debias our dataset. And with generative models, we can see the underlying features in a dataset. And when understanding these features, we can resample specific features in order to have our model be less biased and understand all different images. Let's say we have a facial detection task, which we will actually be performing in one of the labs associated with this lecture. And we can start with different images which are extremely similar, mostly white females with the same skin color, skin tone, and similar poses. On the other hand, we want to be able to represent many different skin tones, many different poses, many illuminations, and lots of different face types. So we want to understand how we can take the different image data that we have in order to have fair and representative models that completely understand everything in our data set so they can correctly classify anything we need to have. And with generative models, we can also detect different outliers because we understand our specific underlying representations. Let's say we're performing a self-driving car task, and most of our driving data that we're going to be training on will be in a sunny environment on a fast-moving highway with a straight road. However, on the edges of our density, we have many other examples where there may be edge cases of a unstraight road, an odd environment, harsh weather where the data may be mutated in some way due to the outside weather, or pedestrians, which will require the car to stop and not continue driving. Finally, with generative models, more recently, we have been able to have generation of different data examples. So with generative models, we can learn the probability distribution of our input data, and that will allow us to create new data instances. For example, now with the rise of ChatGPT and other text generative models, we can create many different modalities like images, videos, text, and much more. Additionally, in biology, some generative models have been used to create different protein structures which can actually cure diseases that were previously thought to be incurable, like cancer. And to perform this generative modeling, we can use different models that work with types of variables called latent variables. So the first type of model are called autoencoders, and the second is generative adversarial networks, or GANs. We're going to take a deep dive into the autoencoder architecture, and more specifically, variational autoencoders, and then we will start looking at GANs and generative adversarial networks to understand how we can implement these models in real life. And I like to use this specific example to understand what a latent variable is. This image is an example image from a story called The Myth of the Cave, which is a very ancient story from one of Plato's original works called The Republic. In this story, we have different prisoners who are kept behind a wall, unable to move, and all they can see is different shadows represented on a wall in front of them. These shadows are created by three-dimensional objects which are behind the wall, and all these prisoners can understand is the two-dimensional shadows that they can see on the wall. These two-dimensional shadows are considered the observational data, which we usually collect, and the 3D images that actually cause these two-dimensional shapes are the latent variables, which represent the dense information where we have many different aspects of the actual image that we want to represent, whereas all we can understand on the surface level is these two-dimensional representations. And what we want to do is to be able to learn these latent or three-dimensional representations only from our observed data. And we can do this using the autoencoder architecture. To start, we use a type of model called the encoder, which takes an input and slowly has more and more dense information until we reach a type of variable called the latent space. This latent space is extremely compressed, and it has the most information dense representation of our original input. Then we can use a decoder to take this latent space and rescale it back up to a output called the reconstructed output, which is a very not information dense output that should be similar to our input, but will not be exactly the same. This allows us to generate new samples. And the best part about this type of model is that when we want to compute the loss, we don't actually have to use labels because this is an unsupervised learning approach. This means that we can directly compare the output to the input to see the differences so we can train our model progressively in order to have a deeper understanding where the input is much closer to the output, but they are slightly different to have that generative capability. And let's simplify all of these compression and decompression layers to a more triangular shape so we can have a simplified representation when we can cover this model in the future. And with our latent space, it has different variables that can be set in order to change the quality of our reconstruction. Let's say we have different images of numbers, and we have this ground truth where all of the numbers are at the highest quality they can be. The lower dimensionality of our latent space, where more and more dense information is represented, the observed data will not be as high quality. So in our two-dimensional latent space, for example, there will be a much more blurry image represented compared to the ground truth, whereas in 5D latent space or five-dimensional space, it would be closer to our original images because there's more dimensionality and more information is represented to allow us to have a more easy to see representation. And with autoencoders, the Z latent space is called the bottleneck hidden layer, where we have our compressed representation learned. When you think of a bottleneck where many different lanes on the highway convene into one, this allows us to have a original, very information, not dense representation and have it strained to a very dense information part where our hidden layer eventually converges at the latent space. Additionally, with our reconstruction loss, we can learn the difference between our output and our input, which allows us to have our latent representation or latent space much more easily represented so we can have as much information about our input data understood. And these models are called autoencoders because they encode the data with the encoder architecture by themselves, which and auto stands for self, so it self-encodes the data. I'd like to introduce a specific type of autoencoder called variational autoencoders, and they advance our autoencoder architecture, which just takes our input, compresses it, and decompresses it to achieve a reconstructed output, and now adds two different variables. These are the mean of our latent space and the standard deviation of our latent space. These two values allow us to introduce some variability into our network, as when we sample from our latent space, we can use these values to take random samples, so that way when we are training our model to have better reconstructed outputs, no specific part of our latent space is relied too heavily on, and we can have a much more even representation. And these are simply adding probability to our autoencoder, where we just randomly sample from our mean and standard deviation to get our latent space sample. And to optimize our variational autoencoder, we can first start by computing the difference between our input and the latent space with our encoder, and then computing the difference between our latent space and the reconstructed output for our decoder. We can combine these two values to achieve a loss, where we are having our representation for the loss with the encoder and decoder loss, where the reconstruction loss is added to a term called the regularization term. Over the next few slides, I'll be getting to this regularization term, but first I want to make sure that you understand that the encoder and decoder are both represented in this loss function, and with the reconstruction and regularization, both the encoder and decoder are represented for. With our reconstruction loss, we can use the comparison between the input and the output squared like we had before. And for our regularization term, we can ensure that our latent space is most similar to the reconstruction, and most of the information from our latent space is represented in the output. And we can do this by creating a specific variable called a prior. And this prior is a type of distribution that we want to model our latent space after. Commonly, we use a type of prior called the normal Gaussian, which looks similar to this circular representation in the graph. This specific prior is most commonly used because when the information is too densely clumped, the representations that are outputted will be exactly the same as our input, whereas if they are too far apart, then our outputs will be random and absolutely unsimilar to our input, and they will not be realistic outputs that are most similar to our inputs. So with our normal Gaussian, it is the best of both worlds by having not too dense and not too far apart representations, so that way our latent space is learned correctly and our outputs of the reconstruction are most similar to the inputs while still being generative. Furthermore, with this normal Gaussian, we can also penalize the network, so that way when it attempts to cluster different points away from our representation of the normal Gaussian, it is unable to do so because this would impact our model, where it memorizes the input data to have a dense representation where the output is exactly the same as the input. And to compute this prior with our reconstruction loss and the regularization term, we can use the Kullback-Leibler divergence, or KL divergence, between our actual latent distribution and the prior. This equation is very complex, and you don't need to understand it bit by bit, but you should understand that this KL divergence value allows us to see how we want our latent space to be most similar to our prior, so that way our representation is correctly created. And to have a more visual example of this regularization term and the prior that we want to use, we want to ensure that the points that we sample from our latent space are continuous, meaning they are similar to each other in the latent space, as well as all of the content is meaningful and is not completely random, meaning it is complete. In the left side, we can have a unregularized latent space where specific examples are close, but they are actually not similar at all to each other. And we have a random squiggle where the point in that latent space is not meaningfully placed and it does not have any true representation. However, on the right, we can see that when it is regularized, the points that are close in latent space are similar and all points are meaningfully created, so that way there is no randomization and each of the points that are similar are created equal. So with our example with different shapes, before a square and a circular triangle were extremely similar, whereas our W-looking squiggle was completely random, whereas in our regularization, our triangle rounded and our perfect triangle were similar, while other shapes were meaningfully put, so that way the farther they are from each other, the less likely they are to be represented closely. And with our regularization, we want to have the best representation so that everything is not too dense, but not also too far apart. So that way we can have specific examples that are perfect, like our triangle, square, and circle. And in between each of those, we can have representations that are meaningfully represented. So that way more circular is closer to the circle, more triangular is more close to the triangle, and etc. for all of the different shapes we may want to have. Using our normal Gaussian allows us to enforce this representation as nothing is too clumped and nothing is too far apart, and our points are correctly created, meaningfully, as well as completely. Now, let's come back to our variational autoencoder, where we have our input compressed to get the latent space, mean, and standard deviation, and then decompressed to achieve our reconstructed output. Again, our loss contains the reconstruction loss with the difference between the output and input, as well as the regularization term to ensure our latent space is correctly created. However, we now have a problem where when we want to train our network, we need to perform a backpropagation representation where we take from our output straight back to the input by computing the weights so we can improve them and have higher accuracy in our latent space. However, we cannot actually compute our gradient value, which is used to optimize our model, through the sampling of our latent space, because these latent space samples are completely random. So rather than using a normal standard backpropagation method, we can use a trick called reparameterization. This is where we have our vector latent sample z as the sum of our mean and our standard deviation, and that standard deviation is scaled by random values from our prior, so that way we can have our z latent space summarized into those two values. So to represent this in a diagram, what we can do is have our input through our z to get an output, and we cannot directly backpropagate this through our z. So what we do is we introduce a new value for our prior as well as this new phi, so that way we can backpropagate through our z by turning it from a stochastic or random to deterministic or not probabilistic random node, and we can backpropagate correctly with reparameterization. Another concept in variational autoencoders is called latent space perturbation, where we want to change different latent variables while keeping all other latent variables in our latent space exactly the same. And let's say we are having a facial detection task where we want to change our head pose as our latent variable. We can start by having it pointed to the left, moving to the center, and then all the way to the right. And this allows us to have different interpretations and different features learned for all of our faces. We also want to do this for latent variables, multiple at the same time, to have them completely uncorrelated with each other, so our model does not relate unrelated specific latent variables together. And let's say, in addition to our head pose, we have a amount of smiling, starting from frowning all the way to grinning. And this allows us to have a process called disentanglement, where different unrelated latent variables or features in our images are not learned in relationship to each other and are rather learned in separation. Again, we can use our latent variables for debiasing because now with our latent variables or the underlying representations in images, we can understand what specific images are underrepresented in a given dataset, and we can sample them more often from our latent space so our model is more diverse and understands all kinds of images. So in summary, for variational autoencoders, we saw how we can compress our representation through images in order to have something our computer and machine can learn. We saw how we can use a trick called Reconstruction for unsupervised learning, where we don't use labels and we simply compare our output directly to our input. We use reparameterization so we can have our backpropagation algorithm correctly work and our model can be trained efficiently for optimization, where we compute our latent space with different values so it can be represented in different parameters instead of having a random sample. We used hidden latent variables, which are the different features we learn, and we had interpretations used with perturbation, so that way the different variables in our latent space can be changed so our model has a diverse image understanding. And finally, we saw how our model can generate new examples of images by taking the input and passing it through to get an output. Now, I want to cover the GAN architecture, or Generative Adversarial Network, which is completely different from a variational autoencoder and sort of has a more interactive and fun approach. So it's very interesting because it is sort of like a cat and mouse game, and I'm going to be going through that in the next few slides. We have a new idea where instead of using variational autoencoders to randomly sample the latent space and achieve new outputs, we just want to randomly sample completely without having any different representations of our latent space and simply just generate new, completely random instances from no training whatsoever. And the problem is that when we want to sample from this complex distribution of randomness, we cannot do this 100% directly. So what we can do is create a simple distribution such as random noise to learn the different representations of our data to generate new samples. The reason our generative adversarial network is generative because part of it is called the generator network, or represented as G, where we start from a random representation of noise, or Z, and we compute a new fake value of capital X fake, which is a random distribution containing different representations where the samples are completely random. Then what we have is now also a discriminator, which takes our fake values, computes them with our actual real values to achieve an output of y, which attempts to identify the different fake from the different real values. We can see how this is like a cat and mouse game where, let's say, you have cops and robbers, and the robbers is the generator, while as the cops are the discriminator. The cops are continuously getting better at catching the robbers when they attempt to rob a bank, let's say, while the robbers or generators are continuously getting better at evading the cops. This is similar to our generative adversarial network, as our generator is continuously getting better at generating random samples close to our actual input data, whereas the discriminator is getting better at identifying fakes from real data. Let's look at a much more concrete representation of this generative adversarial network by taking some example data. Our generator starts by generating new fake data, and because it doesn't understand the representation of the real data, it generates completely random guesses. We look at our discriminator, which takes this fake data as well as new real data into account in order to calculate the probability of which is fake and which is real. So the discriminator starts by predicting extremely randomly what is real and what is fake, and we train it to understand what is fake, and it progressively gets better at identifying that the green points are real and the pink points are fake. Then our generator comes back, sees what the real data is, and attempts to improve its imitation by moving these points from farther away to closer to the real data. Then it keeps moving them closer and closer through our discriminator rounds, and the discriminator again tries to predict what is real and what is fake. It again predicts which ones are real accurately and which ones are fake accurately, and continuously trains in order to understand what is specifically fake and what is real. So it gets better and better until eventually it understands what is real and what is fake. The generator gets better, however, and it keeps moving these samples closer to the real data until eventually it reaches a different but very similar representation, and our discriminator is unable to understand what is real and what is fake, meaning our generator has succeeded. We can then detach our generator and use it in real-world applications to create new samples, new generated images that are actually extremely lifelike. As I said at the beginning of this part of the lecture, we actually saw how the generator, or the GAN, was used to generate new faces that seemed extremely realistic, whereas the faces were actually completely fake. So again, remember that our discriminator inside of the generative adversarial network works to identify real from fake data, and the fakes are generated by our generator, which attempts to imitate the real data to trick our discriminator. And to train this, we want to understand that our discriminator wants to get better at identifying real from fake, and our generator wants to get better at creating fakes more similar to the reals. So for our discriminator, we can find the maximum where our representation is the best discriminator to tell the difference between the fake and real, whereas for our generator, we want to have our generator have the least probability of being identifiable between the fake and real. We can combine this loss function for the generator and discriminator to see that both of them can be combined, where we want to have our generator have the lowest loss, our discriminator also have the lowest loss, where the discriminator is best at predicting real from fake, and the generator is best at generating new fake data samples that are most similar to the real data. And when we are generating new data with our generative adversarial network, we train our generator network with new data that has never been seen before, and it can generate new samples. And this introduces something very interesting, because let's say we have our noise, which is completely random, and we get two different samples from it, and we pass them through our generator to get an image of a duck inside of our target data distribution, which is the reconstructions, and we also get a Finch at a different point in our noise. Now, we can see the difference between these noises as well as the target data, and we can now move between these different parts of the space, and we can have different parts of each image included. So from the left, we have our original image of the duck, and on the right, we have the original image of the bird. And as we get closer to the middle, we can see that both images are somewhat combined in order to have examples from both. This is extremely important because let's say when you generate two images, you like both of them, but you want them to have combined aspects from each other. So you can use this idea of moving between two different points in order to get something in the middle. And with our generative adversarial networks, because they work so well, there have been many different applications. For example, for facial generation, which we examined, there is actually a type of architecture called CycleGAN, which works to generate new images based on random data. So here we have the generator and discriminator with our latent space, which originally starts with a very small space and moves progressively closer to getting a higher and higher dimensionality representation to create very realistic looking images, such as these we can see on the left. And as a result, we have many different images that are severely realistic, and sometimes this can actually introduce problems where we have now things in society like deepfakes and other issues with this computer vision and generation, where some things are generated so realistic that now it's actually difficult to determine what is real and what is fake, similar to the discriminator. And with a new GAN architecture, we can introduce a condition where we can change our output by conditioning it with a specific factor. This factor could be called C, and it would allow us to only take specific parts of our output. And let's say that we want to convert from a specific representation of different parts of an image, and we want to have a generator that takes this representation and turns it to an actual image. Then our discriminator wants to compare between this representation as well as the actual generated images. We want to see if the original representation we wanted to generate is actually comparable to what was generated. This is called pix to pix, where we sort of translate these two representations together. And this can actually be used to convert different views from satellites into more colorful representations that you can see on Google Maps. So when you change your map representation from the actual satellite data to the more simple representation of blocks, it actually uses an AI model that sees what specific roofs look like, as well as what grassy areas look like, to convert from a map to a satellite data, or from satellite data to a map. And as I said, the cycle GAN architecture works by taking an input and continuously mapping between two different spaces, where the generator and the discriminator both work together in order to map one input to a new output space. In fact, in the deep learning course, they created a video where a horse running in a field was actually converted to a zebra, and the environment is very similar, but it almost seems like the zebra is actually running around the field, and the environment even changes. As you can see, the grass was originally greener and the trees were brighter, whereas in the zebra part of the you've generated video, the grass is darker and the trees are darker, similar to the zebra's natural environment. And the difference between a GAN and a cycle GAN is that our original generative adversarial networks work from random distributions to create an output, whereas our cycle GANs are working with an input and mapping it to an output, going back and forth to have different mappings between two parts of our data. And cycle GANs can actually be used for translation between audios and spectrograms, and the spectrograms can be generated to convert to new audio. In our last lecture, we looked at recurrent neural networks to generate music, where we worked with a textual format called ABC. And with this cycle GAN, we could actually use an audio waveform, convert it to a spectrogram, generate new spectrograms, and convert it to an audio waveform that can actually be played. And in fact, for the Introduction to Deep Learning course, they generated a video of President Obama by using this kind of architecture, where they recorded a video and a sound of one of the instructors. They converted it to a spectrogram, converted it to a spectrogram similar to President Obama, and finally got the audio waveform that sounds extremely realistic, is as if President Obama was actually speaking. So now let's conclude by covering what we've gotten through so far. With autoencoders and variational autoencoders, we saw how we can have our original high-dimensional input converted to a very dense representation in the latent space, and then move it back to a reconstructed high-dimensional output that is similar to our input, but is not slightly distinct, in order to have a generative capability. Then we investigated generative adversarial networks, or GANs, which use a cat and mouse situation between the generator and discriminator, where the generator identifies and creates fake data, whereas the discriminator tells the difference between real data and fake data, in order to ensure that we have an accurate generator that can generate realistic samples.